Hello all, welcome to this video on System Software Lab. Today I'll be talking about SIC Relocating Loader with Bitmask and its implementation in C. Let us begin by looking into the SIC architecture. Now the SIC memory consists of 8 bit bytes. Any consecutive 3 bytes will form a word. All the addresses are byte addresses. Now the words are addressed by the location of their lowest numbered byte. There are a total of 32,768 or 2 raised to 15 bytes in the computer memory. Now looking into its instruction format, all the instructions will have a 24-bit format. As shown here, the first 8 bits will stand for the opcode and the next bit will indicate whether the addressing mode is indexed or not, and the rest 15 bits will be used for the address. Now there are two addressing modes in SIC, the one being direct addressing mode and the next being the indexed addressing mode. Now we'll look into SIC XE architecture. Now here the maximum memory available is 2 raised to 20 bytes. Now this leads to a change in the instruction format and addressing modes. The larger memory available in SIC XE means that an address will in general no longer fit into the 15-bit field. Thus, the instruction format used on a standard version of SIC is no longer suitable. Now, looking into the instruction format, there are two possible options here. Either we need to use some kind of relative addressing or extend the address field to 20 bits. Now, that is done in format 3 and 4 of SIC XE. And there are some cases that do not need any reference memory at all. That is the format 1 and 2 in SIC XE. Now there is a bit E that is used to differentiate between format 3 and 4. Thus E will be 0 for format 3 and 1 for format 4. Now we look into the different addressing modes of SIC XE. The first one is format 1, which will contain 1 byte instruction. So there the 8 bits will be used for the opcode. An example of this is rsub, which is return to subroutine instruction. Next we have format 2, where we have 2 bytes. So looking into the format, 8 bits for the opcode, 4 bits each for the 2 operands there. An example will be COMPR A, S. Then there is format 3, where there will be 3 bytes. So there the format will be 6 bits for the opcode and another 6 bits reserved for extra information on the instruction, namely N, which gives information about the indirect addressing, I for immediate addressing, X for indexed addressing, B for base relative addressing, P for program counter relative addressing, and E, which denotes whether the instruction is format 3 or 4, and finally the displacement, which is given in 12 bits. Now an example for this is LDA #3. Now there are two relative addressing modes in SIC XE, one being the base relative and second being the program counter relative. Now these are the bits that will give extra information on the instruction format 3 and 4. Now when we look into the base relative addressing, the disp field, this in format 3 instruction is interpreted as a 12-bit unsigned integer. Now if it is program counter relative addressing, then this field will be interpreted as a 12-bit signed integer with negative values represented in 2's complement form. Now if the bits B and P are set to 0, Then the displacement field of format 3 will be taken as the target address. Now SIC instructions that will specify neither the immediate nor indexed addressing are assembled with bits n and I, both which will be set as 1. Now the assemblers for standard version of SIC will set the bits n and I to 0. Now this is because 8-bit binary codes for all SIC instructions end in 00. Now if the bits n and I are both 0, then B, P and E will be considered a part of the address field of the instruction. Now the format 3 is identical to format used on the standard version of SIC XE. Now looking into format 4, which will have 4 bytes. Looking into the format, 6 bits for the opcode, then extra information bits N, I, X, B, P, E and 20-bit address. An example for this is plus J sub read record. Now if the bits B and P are set to 0, then the target address will be taken from the address field of the instruction, which is the 20-bit address. Now this is called direct addressing to distinguish it from the relative addressing mode. Now any of the addressing modes can be combined with indexed addressing here. In both format 3 and 4, if the X bit is 1, then the term X is added along with the target address calculation. Now the standard version of SIC machine uses only direct addressing, whether it is with or without indexing. Now bits I and N in format 3 and 4 are used to specify how the target address is used. Now if I is 1 and N is 0, then the target address will be used as operand value. No memory reference is performed here. Now this is immediate addressing. Now if the I value is 0 and N value is 1, then the word at the location will be given by the target address. That is, the value in it will be taken as address of the operand value. Now this is called indirect addressing. Now if both I and N are 0 or 1, then the target address is taken as the location of the operand. Now that is a simple addressing mode. There is no indexing in both immediate or indirect addressing. So here the direct address is only available in format 4 of SIC XE and direct addressing of SIC. So those will be the two cases where the relocation is happening. Now we look into what relocation is. Relocatable means it refers to something that can be moved without adjustment. That is, the program semantics are not changed by moving the item. For simple SIC, most instructions use absolute referencing, and so most operands are not relocatable. In contrast, most SIC XE operands are relocatable, the exception being the 4-byte instructions, which usually have operands that are not relocatable. Symbols such as the statement labels and self-defining literals have a value that is relative to the start statement. Now these are called relative references. Now when a relative reference is used in an absolute context, it is not relocatable. For example, plus LDA hash stuff. Now here the operand stuff, that is a relative reference, it is not relocatable. A reference whose values does not depend on the start statement is called an absolute reference. Actual numbers are always absolute references. So in contrast, plus LDA hash 1234 has a relocatable operand. Note that LDA 1234 is relocatable for either symbol SIC or SIC XE. Now we look into a relocating loader or a relative loader. This allows modules to be loaded into any location in main memory but not moved after initial loading. Location is determined at load time. The addresses in the code are all relative. The load module format must identify the locations of addresses that need relocation and the basis to which they are relative. This allows programs to be loaded at different locations in memory. Now looking into the dynamic relocating loader, it allows the module to be moved after initial loading, and this needs the support of swapping. The addresses are kept in relative form. Base is added to the address at runtime. Special hardware is needed in this case. Now this allowed programs to be loaded at one location, swapped out and then reloaded to different location in memory. This function was essential for the development of variable partition multiprogramming. Multiprogramming with variable partitioning is a contiguous memory management technique in which the main memory is not divided into partitions and the process is allocated a chunk of free memory that is big enough for it to fit. The space which is left is considered as the free space, which can be further used for other processes. It also provides the concept of compaction. With the development of hardware support for virtual memory, swapping could be performed without asking the loader to do relocation. Now we look into the different relocation methods. Now the first one is modification record and the second one is relocation bit, which we will be discussing in this video. Now here we have a 12-bit mask that is used for each text record. Now looking into the values each column will specify. It is similar to the normal text record format. It is just that we have an additional information which stands for the relocation bit mask. The first column will stand for T, which denotes that it's a text record. Columns 2 to 7 will contain the starting address. Columns 8 to 9 will contain the length in bytes. And column 10 to 12 will contain the relocation bits. Finally, column 13 to 72 will contain the object code. Now we'll look into detail what a relocation bit mask is. On a machine that primarily uses direct addressing and has a fixed instruction format, it is often more efficient to specify relocation using relocation bits. Here there are no modification records. The text records are the same as before, except that there is a relocation bit associated with each word of the object code. Since all the SIC instructions occupy one word, this means that there is one relocation bit for each possible instruction. Now the meaning of this is, if we look into the format for the relocation mask, here we already discussed that it will be a 12-bit mask value. So for example, in this case, we have the bit mask as FFC. Now expanding it into 12-bit, F will become 1111. Second F will also be 1111 and C will be 12, so 1100. Now, the maximum number of records in a text record is 10. Now, the relocation bits will be of length. The maximum length is 12. So, in this case, we have the last two digits in C as 0. So, we can take only the 10 values will be marked as 1. So, all the records need to be modified. So, you can see that each of these bits in the bit mask is associated with 4 records each because F can be expanded as 1111. So each one will correspond to each of these object words here. So since one relocation bit will correspond to 4 of such records, so each record will have 6 bits each. So 6 into 4 is 24, which means we have 3 bytes of object program code that is associated with each relocation bit mask. Now the relocation bits here will be gathered together into a bit mask following the length indicator in each text record. Now the mask here will be represented in the form of a 3 hexadecimal digit, which is given here. Now, if the relocation bit corresponding to a word of object code is set to 1, then the program's starting address is to be added to this word when the program is relocated. A bit value of 0 indicates that no modification is necessary. If a text record contains less than 12 words of object code, then the bits corresponding to the unused words are set to 0. Some computers provide a hardware relocation capability that eliminates some of the need for the loader to perform program relocation. For example, some such machines consider all memory references to be relative to the beginning of the user's assigned area of memory. Now, the conversion of these relative addresses to actual addresses is performed as the program is executed. Now, we'll look into the algorithm. Now, it begins by getting the address to which the program is to be relocated from the operating system. So, in our program, it will be asked to the programmer. Next, it is reading out each record. It's checking if it's the end record, and if it's the text record, what it does is it will take the length of the text record from that particular row, and it will also extract the mask bits. Now it will take the length of the text record as the loop control variable. Then it will take each mask bit and compare and see if it is 1 or 0. Now if it is 1, it will add the program address which was received from the OS or from the programmer to the specified address, and it means the modification is necessary there. Now if the bit mask is 0, the object code will be simply moved to that location. No modification will be done in the record. This will become clearer when I'll discuss in detail how this is happening in the code here. Now this is the relocatable program for SIC that we'll be using in this program. We have the object code, and note that the starting address of the program is 0. Then we have the object program with the relocation bit mask, which I discussed before. Now as said, the bit mask FFC in the first text rod specify that all the 10 words of the object code needs to be modified here. Then now taking the second entry in the text record E00, it specifies that the first 3 words need to be modified because E stands for 14, which is 1110. So 111 and the rest are the zeros. So no modification needed. Now the remainder of the object code in this record will represent the data constants. Now we look this area in the code here. We'll see that starting from this address we have some data constants. So no modifications is necessary there. Now the other text records will follow the same pattern. Also we can see here that even though there is room for a record to be stored here, this particular instruction was generated as a new text record. This is for the LDX instruction in the program we saw before. Now this occurs due to the same reason I explained before, where each relocation bit is associated with a 3 byte segment of the object code in the text record. Now any value that is to be modified during relocation must be coinciding with one of these 3 byte segments so that it corresponds to the particular relocation bit. Now the assembled LDX instruction does require modification because of its direct address. However, if it were placed in the preceding text record, what will happen is it would not be properly aligned to correspond to a relocation bit there, because there is a 1 byte data value that is generated after, which is this F1. Now this is the output for the relocating loader with relocation bit mask. Now this looks similar to the output of the absolute loader. In the previous video I discussed about the same. Now here the difference will be in this final location, and also some of the locations where we have the operand address will be added along with the address obtained from the user. For example, if we look here the first value 140033 is to be modified because the relocation bit is 1 there. If you see here, it is modified as 145033. Similarly, we saw that in case of a data constant in the second text record, starting from here, no modification was necessary. That is reflected as such here. 5000 is not added to any of these values. Now we look into the program logic. As discussed in the algorithm, first we'll get the location to where the program is to be relocated, which will be mentioned as start. Now while reading the data from the input file that we are going to provide, which looks something like this, first what it does is it will read the string that is in the starting of the record. Here it is H. Now this input is read to see what kind of record is it, whether it's a header, text, or an end record. So by reading the string value in the beginning of the record, which here we call by the variable name input, the programmer comes to know that it is a header record. So what he does is he'll read the values that comes after it, which is the control section name, the starting address, the length of the object code, which is this, and then finally there is another variable input. Now this input will be reading the string in the next line because there is no string value following the length of the text record, which is T. So that will give an indication of what kind of record comes next, whether it's a text or not. Now if it is a text record, what are the values following it? It will be the text address, then we have the text length, and finally the bit mask there. Now what happens is the text address will be added to the starting address. So that will be the final location to where the program is to be relocated. The starting address that is got from the programmer and the address from where the text record is beginning. Then the next step is to convert the bit mask, relocation bit mask, into the corresponding bits, which will be done by a function named as mask to bit. Then, as discussed before, the maximum length of a text record is 10. So the number of bits in the relocation bit mask can go up to 12. So if in any case if it's 12, it will be resized to 10 to match it with the text record. There are two cases that can arise here. In one case, this mask length can go beyond the number of object words. So in that case, the mask length will be kept as the limit of the loop. So if it's the other case, that is if the number of object words is greater than or equal to the mask length, after the modification is performed on the object codes that are marked with 1, the rest of the code will be displayed as such without any change. Then what we do next is we have resolved everything till the conversion of bit mask. Now we'll read the data after it, which is the object words. Usually the object word is a continuous 6-bit word. It is read as a single word, usually as a string. Here, since there can be modification in the record, I have modeled it as this, where I'll read the opcode followed by the operand address. This address is separated because in case if there is any modification happening, the start address will be added to this location. If there is no modification, it is displayed as such. So I have separated it out like this. So this will be the opcodes in each of the record followed by the operand address. Now when each of these set of record is read, it will check the relocation bit and see if relocation is needed. If relocation is needed, the start address will be added to this case, or the address will be, that is the value here will be the same. Now the relocated address and content will be written to the file because it can exceed what we see on the terminal. Here the file will be output.txt. Now this is the program. This is the program input which we discussed before, followed by the program output. So it is an SIC relocating loader with a bit mask. Now the address to which the relocation should happen is asked to the programmer. Here it is 5000, and we'll see the relocated address to where the relocation happens and also the content. As discussed before, this record was needing a relocation, so it was 140033. Since relocation is needed, it became 145033. Similarly, in this case, 4C0000, it was a data constant. No modification was necessary, so the data was taken as such. Though the address to which they relocated changes. Here it will be 5000 instead of 0, and here it will be 5027. Now we'll see a demo on how this is done. So initially I have the relocation loader program and the input, which is the object code here. And this is the program we just saw before. This is the input file. Next I'll compile the program, which is named as relocloader.c. After that, I run the program. So I'm asked the address to which the relocation should happen. It is 5000. So this is the answer. Since it exceeds the terminal size, I have written into a file called as output.txt, which can be seen here. That's all for now. Thank you for watching.